Hi, everyone. Welcome to this week's edition of HoloTube. And we are very happy to have Eric Mefford from the University of Victoria and the Pacific Northwest. And we are looking forward to your talk. Eric, the stage is yours.
Great, thank you. And thanks to the organizers for the invitation. So today I'm going to talk about this paper that I wrote with Richard Davison and Blaise Gouthereau, which has the same title as the talk, where we try and understand the appearance of a sound mode at zero temperature in certain models of Einstein-Maxwell dilaton gravity. Okay, so I was encouraged to give a little bit of background introduction, and at the risk of sounding grandiose, I decided to introduce these two plots, which are two of the most famous observations in the hole-doped cuprates. On the left, the plot shows the famous linear in temperature resistivity, and on the right, the plot shows the famous quadratic in temperature Hall angle. And I don't want to give the impression that I'm going to explain these exactly, but they should serve as kind of a motivation for the work, something to keep in the back of your mind. Now, to understand why these observations are so intriguing, it'll be useful to kind of set up a straw man for what a metal is and try and pick that apart. So if you were to pick up a textbook, let's say Ashcroft and Merman, you might walk away with the impression that a metal is a dilute electron fluid, which is interacting with some regular periodic array of positive ions whose electric resistance increases with temperature with specific powers due to Fermi Dirac statistics. So in a little more detail, when we think of a metal, we care about an increasing resistance, and at the longest scales, latest times, we want to simplify things and think about it in terms of just a single scattering time scale. So we think of a current which degrades over time and relaxes to equilibrium set by a single time scale. And this time scale can be estimated using simple physics. To get a sense of scales in the problem, there's two important temperatures. There's the Debye temperature, which is roughly characterizing the inverse lattice scale. And then there's also the Fermi temperature, which is characterizing the density of electrons. And you can tell already that these two numbers are quite different. So there's already a separation of scales. And then typically we observe metals, we measure their resistance at lower temperatures. And in that regime, the Fermi Dirac distribution is approximately a step function, but it's been broadened a little bit on a scale of order of the temperature. And so when we think about scattering, we think about, for instance, two electrons interacting with each other, and they're constrained by the phase space at low temperatures. There's roughly order temperature states available to scatter from and into. So for electron-electron scattering, you end up with just a t² behavior in the resistivity. But at even lower temperatures, because of the diluteness of the electron fluid, it's unlikely for this electron-electron interaction to happen. And instead what happens is an electron scatters off the lattice, creates a phonon, and loses its, degrades its current that way. And this interaction depends on the momentum, which is on the scale of the temperature. And then there's also an extra reduced phase space. So the scattering tends to happen in the forward direction. And that factor of temperature plus a factor of t² from forward scattering plus the t² from the phase space of the electrons ends up giving just this famous block t⁵ law. And so at low temperatures, there's two powers we expect to see, at least in the simplest model of metals, a t⁵ and a t². If we went to even lower temperatures, there might be some residual resistance from impurities or disorder. Okay. But if we return to this linear in temperature resistivity, we see that, well, it's really weird. It's strange. And it's strange because, well, one, we don't see a t to the fifth or a t squared. Of course, we made a lot of approximations, simplifying assumptions in deriving the t squared and t to the fifth. So maybe it's not surprising that we don't get exactly the power law from a simple metal. But what's even more unusual is that the resistivity is linear over many orders of magnitude, and it seems to have the same slope. And it has the same slope at low temperatures. We could, in near optimal doping in the cleanest samples, this curve seems to go all the way to 0 temperature. And it has the same slope at high temperatures. And that suggests that there's some sort of universal scattering mechanism. And if you were to take the Drude formula for the resistivity, which is basically the formula assuming a single scattering time, you would find that the scattering time, the time scale, has this behavior. It's h bar over kBt. And this is a type of time that Planck might have written down. And so this time scale has been called Planckian dissipation. For those of us in the holography community, when we see this time scale, we probably think of a picture like this. So we know that in certain probes of quantum correlations in holographic matter, the correlation functions, or certain kind of complex correlation functions, seem to decay over a characteristic timescale, which you can see is exactly this timescale. And so that's one intriguing result from the linear temperature resistivity that kind of at least attracts me to the problem. But if you look at this curve, it's more than just strange, it's also bad. And the reason it's bad is because it crosses this MIR bound. And this is kind of a vague notion, a vague upper boundary to the resistivity, but it's roughly saying that the localization of wave packets is getting smaller than the lattice scale. And so if we were thinking of resistivity as coming from quasi-particle scattering, well, it's very intriguing and kind of counterintuitive that you could localize a quasi-particle at a scale smaller than the lattice scale. And so more likely than not, this curve is indicating that whatever is transporting the charge is not quasi-particle in nature. And just to emphasize that this is actually a useful paradigm, if we looked at simple metals or alloys, you see that they actually do tend to asymptote or plateau at some level, which is roughly the same lattice scale. Okay, so we have a universal scattering mechanism, or seemingly a universal scattering mechanism. It has a power law. There's no quasi-particles. Many of us would naturally jump to the idea that this scattering can come from quantum criticality. And if you haven't seen quantum criticality before, what it says is that the resistivity or the correlation functions have a very simple form that scales with the power of the energy scale, where the power that appears here depends on the spectrum of low-lying operators around the critical point. And then there's this function, f, which is a function of time and space, but we can estimate what it is by using the correlation length, so the typical scale of correlations in the problem. And then we make it dimensionless with powers of the temperature. So the time argument scales with z. This is the dynamical critical exponent compared to the spatial argument. And what's special about this function is that for systems which are described by quantum criticality or a quantum critical point, this particular behavior does better and better at describing the system, where it covers a larger region of the phase diagram at higher temperatures. And the reason for that is that if there's a quantum critical point, well, as you tune some external parameter, there can be a critical point where on either side of the critical point, there are two different phases at 0 temperature. And as you tune this parameter, the correlation length tends to diverge as some power of the distance from the the critical point. And if you look at this function, that means the arguments are getting very large. So as we increase the temperature, you can see that I can make psi smaller and smaller because it's being compensated by the temperature. And so if quantum criticality is important for the resistivity, we would expect to see some quantum critical fan opening up as we go to higher temperatures. And that's exactly what we see in the hole doped cuprates. So in this plot, the colors correspond to the power being fit to experimental data for the resistivity. Red indicates linear in temperature. Blue indicates quadratic in temperature. So this is like Fermi liquid behavior, like I discussed earlier. And you can see that at high temperatures, there's a larger region, which is roughly scaling like linear in the temperature. Then it seems like the fan starts to decrease. But there's actually this intriguing feature at low temperatures where there's this kind of broad region, which is also linear in temperature. And it's an open question what's going on here, but perhaps it's a line of critical points. This is something I'll come back to at the end of the talk. Okay, so with quantum criticality, what you want to do is understand kind of the scaling behavior at low temperatures, and that's something that these authors try to do for the cuprates. And you want to find kind of the minimal ingredients necessary to describe certain correlation functions. So if we take a length scaling to go like -1, then like I said earlier, time can scale with a different power, which we'll call the dynamical critical exponent z. The entropy density scales like the dimension as per usual, but then we can introduce another critical exponent, which we call the hyperscaling violation parameter. And this describes roughly the dimensionality of the system at low temperatures. So for instance, in a Fermi liquid, excitations about the Fermi surface are effectively one-dimensional, which means that this theta is d-1 for a Fermi liquid. We can also introduce another critical exponent or anomalous scaling dimension for the charge density, which will be this capital phi. And from these four ingredients, we can derive scaling dimensions for other transport quantities. So for instance, the energy density scales like d plus z minus theta. From charge conservation, the spatial component of the current scales like d minus theta plus phi plus z minus 1. And from energy conservation, the heat current scales like d minus theta plus 2z minus 1. And we can combine these two using Joule heating to derive the scaling dimension for the electric field. And then from there, derive the scaling dimension for the magnetic field. And combining all of this, we get certain scalings for the resistivity and for the Hall angle. And the minimal set of scaling dimensions that is necessary for a scaling theory to describe the linear and temperature resistivity and the Hall angle ends up being just a dynamical critical exponent of 4/3 and this anomalous scaling dimension for the charge of -2/3 with hyperscaling being set to 0. Okay. In this derivation, there's a fundamental assumption that there are no long-lived operators which overlap with the heat or electric currents. And so what I mean by that is we can write an equation similar to the one I wrote for the electric current earlier, which says that there's some operator whose expectation value decreases over time. It relaxes with some time scale that scales like something greater than 1 over the temperature. So at finite temperature, we expect that at least locally, the system will relax on scales of order the temperature. So this equation is just saying that we're assuming there's nothing that is going to scale or relax slower than that. And then the fact that if an operator like this did exist, we would require that it doesn't appear in any correlation functions with the current or heat current, meaning the susceptibilities vanish. An important operator like this would be the momentum, because in a relativistic invariant system, we would expect that chi jp and chi jqp don't vanish. And so if it's the case that there's no long-lived momentum, then we assume translations should be strongly broken. Nevertheless, we can have an electric current because we can define something called the incoherent current, which is given by chi pp, the momentum susceptibility, times the electric current, minus chi jp times the momentum. And this combination of currents automatically satisfies chi j inc p equals 0. And so if this is involved in, if there's an incoherent current in the cuprates, what we should see is some broad, featureless optical conductivity. And that's exactly what we see. So here, these are plots of the optical conductivity in LSCO for various dopings. These peaks here are optical phonons, but you can see that there's this background, which is very broad and roughly featureless. So all of these together kind of giving a picture for what we might expect in the cuprates. It's natural to ask, well, can we do something similar in holography? And this was asked almost 10 years ago. The answer is yes. So using a Einstein-Maxwell-Dilaton action plus axions. So here, this action includes the Ricci scalar R. It includes a Maxwell field through the F squared. It includes a neutral scalar, which we call the dilaton, which has some potential. And it includes some massless real scalars, which we call axions, which have an expectation value, which is linearly dependent on the spatial coordinates. So these break translations, but do so homogeneously. And then finally, the dilaton can couple to the axions and to the Maxwell term with some function y and z. And in this model, you can analytically derive both the DC conductivity and the Hall angle, and they take this form. So the DC conductivity has two parts. The first part is this z of phi, the coupling of f squared. The second part depends on k squared, the axions, and this y of phi. And it's natural to kind of think of these two terms as capturing the incoherent part of the conductivity and a dissipative part. And if we call this piece the dissipative part, because it depends on k squared, so it depends on the scale of translation breaking, then the Hall angle is directly proportional to only this. I should say that this kind of distinction between dissipative and incoherent doesn't exactly separate into just z and this term. It's a little more subtle. I'll refer you to this paper, but at least for strong momentum relaxation, this separation is roughly correct. Okay, so if you want two different scaling behaviors for the Hall angle and the resistivity, you can see from this form that in the conductivity, we want z of phi to dominate. And then we can choose whatever scaling behavior we want for the Hall angle. And a very natural way to do this is to just break translation strongly. So make this k squared y very large. And that tells us that in the resistivity, the incoherent current will dominate. So there's two natural questions that arise from this analysis. One is just how can we make this z of phi very large? But then also, if we look at the cuprates, we can see that we can make very clean materials, which have, effectively very small impurities. And so That's kind of in tension with the strong momentum relaxation. And it's a natural question how to make this ZFI dominate even in the presence of weak momentum relaxation or even translation invariance. And what was found by these authors is that this is possible in these Einstein-Maxwell-Dilaton theories. But when you do this, you get an emergent long-lived mode, which overlaps with the current. And furthermore, because of what I said earlier, where in the scaling analysis, the requirement was that there were no operators which are especially long-lived that overlap with the current, here, that's being violated. And so we would expect that the scaling theory is slightly different. And what these authors found was that the incoherent current does indeed have a different scaling dimension than expected from a naive scaling analysis. And this behavior has been called dangerously irrelevant. The reason is, well, what's going on is there's the electric part, the Maxwell part of the action is becoming negligible in the IR, but it still seems to control some dissipative transport and then also change the scaling behavior at low energies. Okay. So in these models, there's some emergent long-lived mode. And if you've been working in holography long enough, that might make you think of probe brains. So in probe brains a long time ago, it was discovered that at low temperatures, there is a sound mode, which has been called zero sound. Zero sound is just a linearly propagating mode of the Fermi surface, which, zero sound is a linearly propagating mode of the Fermi surface, which, I mean, in these holographic models, there's no Fermi surface. So instead, in these holographic models, what was found is that at zero temperature, there's a propagating sound mode, which, as we increase the temperature, seems to move up the imaginary axis and collide. And then at finite temperatures, or at higher temperatures, forms a diffusive mode and a gapped mode. Now, in these probe brains, this alpha prime kind of controls the non-linearities. And so if we make alpha prime very small, what we end up with is something that looks like an Einstein-Maxwell theory. And it was found by some other authors that at low temperatures in Einstein-Maxwell theories, you also have a zero temperature sound mode. But in that case, there's no emergent long-lived mode, which is characterized by this gap pole. Instead, you just get sound modes which move up the imaginary axis, and a diffusive mode which sticks around. Okay, so in these Einstein-Maxwell-Dilaton theories, you see something very similar to the large alpha prime version of the probe brains. Here, what I've plotted is two different numerical results for the quasi-normal modes in a model of Einstein-Maxwell-Dilaton gravity, which I'll show you in a second. So at low temperatures, at low values of the wave number or high values of the temperature, you can see that there's a gapped mode here and a diffusive mode. And as we decrease the temperature or increase the wave number, these two modes collide and they form a propagating mode, which has a linear dispersion. And so this is a sound mode. And you can see that as I decrease the temperature, I stick in this region of the diagram. And so we expect that in these models, there's a sound mode. Oh, there's a question. Yes.
Yeah, I have a question concerning the previous slide. When you have this typical behavior in this middle graphics probe brain model, it's a typical behavior of a kind of phase transition. Did you identify this kind of phase transition here? So that you have this transition from this mode which are coming from the sides, colliding, and then they are moving along a certain axis here, maybe the imaginary axis. Did you
so
identify this phase transition?
In these models, the arrows are indicating increasing temperature.
Yeah, okay.
So yeah, you might have expected that, if I understand your question correctly, this mode moving up the axis is like looking like something that's trying to become unstable. Is that?
Yeah, but no, it's a typical behavior in the PT symmetric theory. They have a similar behavior. You have colliding pairs of eigenvalues, which are on the one side of the PT phase transition, they are complex conjugate pairs, and then they are reforming in a pair of purely real or purely imaginary eigenvalues. And you have here the same behavior, actually. So it's very likely that you have in this certain regime a kind of hidden PT symmetry there in your model. It's just a comment. I was just wondering whether you already identified this behavior.
Well, there is PT symmetry here, and that's why there's sound modes that appear at both plus and minus omega, real omega.
Yeah.
As far as a phase transition, what I'm going to argue, at least in the Einstein-Maxwell-Dilaton theories, is that what you're seeing, okay, so as you lower the temperature, the arrows go the other way. What you're seeing is that there's this emergent symmetry that's appearing.
Yeah, sure, yes. And you can reformulate this as a kind of local PT symmetry, but it's just a comment. I was just wondering whether you did already identify this as a PT phase transition. Yeah.
I don't think so, but I'll,
Okay, obviously not yet. Okay, thank you.
Yeah, thanks.
The symmetries would have to be different on the two sides of the transition, right?
Mm-hmm.
Like there would have to be a symmetry broken, and that is something I suppose that Günther Uwe is suggesting to check.
Yeah, you can. It's obvious from the pictures. It's a typical picture from PT symmetric phase transitions here. So
yes.
It's for PT people, it's nothing special. So I'm just wondering whether you already identified this link to PT symmetry here.
I see.
Okay, it was just a comment.
Yeah, maybe we can chat about it after the talk.
Yeah. Okay. Thank you.
I don't think it's something we've thought about.
Okay. Thank you.
Okay. So in these Einstein-Maxwell-Dilaton theories, you see something similar. You see a gapped mode and a diffusive mode. They collide and they form a propagating mode. And the two plots here are at different values of J, which is roughly characterizing the scale of broken conformal variance in the in the UV. And so the two plots are just showing or emphasizing that at low temperatures, really, it's the IR physics which is important. You get the same behavior for different UV sources. Okay, so now I'm going to try and kind of understand this picture a little more. And what we're going to do is we're going to go to a probe brain, a probe Maxwell field. But before I do so, I want to talk a little bit more about the geometries. So in these Einstein-Maxwell-Dilaton theories, here I've written the action. This is essentially the action that I wrote before, but I've turned the axions off. So translation invariance is preserved. If you choose a particular functional form for the scalar potential and for the coupling of the Maxwell field, such that they have exponential behavior in the IR, then you can find solutions where the dilaton scales logarithmically, meaning that these functions, when you plug this in, scale as power laws in a radial coordinate r, which is an emergent radial coordinate in the IR. And choosing z to become very large, that's where we have this incoherent current dominating, or this emergent long-lived mode, is equivalent to setting the Maxwell field, or you can find that the Maxwell field has a particular radial behavior in the IR, which is becoming very small. So this kappa gamma is roughly this z. It's positive and it's much larger than these values here. And so this is telling you that the Maxwell part of this action is becoming irrelevant in the IR. And when that happens, you can find the IR geometries using just the dilaton part of the action. And they have this particular behavior. They are power laws in R, where there's an emergent scale covariance. So if I take R to lambda R, you can see that this piece here is invariant. Here, I take R to lambda R, and I can scale X to lambda X. This will be invariant. Here, R to lambda R requires that I scale T to lambda to the Z times T. But then there's this overall factor out front, which tells you that rather than this metric being invariant under this scaling transformation, it's covariant. It scales with theta. And each of these exponents, z and theta, are the exponents that appeared earlier characterizing the quantum critical point. Furthermore, you can find these exponents just using the properties of these potentials. So theta, the hyperscaling violation parameter, is just given roughly by kappa times delta, and then z, the dynamical critical exponent, is proportional to kappa squared once you've subtracted off theta. So we're going to work in these geometries, but we're actually going to turn off the completely, or rather what we actually do is we just add a second Maxwell field to probe the system. And what we find is that the quasi-normal modes have the same behavior as before. There's a gapped mode and a diffusive mode at low values of k that move up the imaginary axis, collide, and form a propagating mode. And this behavior can be described in terms of two equations. There's the standard U1 current conservation, U1 charge conservation, and then a second equation, which is roughly a constitutive relation for the spatial current, but it includes an extra piece, which is a higher derivative correction that has a coefficient tau. And it's important that in this equation, this term here is much larger than any other higher derivative correction. We can find what tau is from the bulk. It's given by the DC conductivity divided by the current susceptibility. Each of these are given by bulk quantities. So the DC conductivity is given by the value of the coupling Z and C. This is the spatial component of the metric on the horizon. And chi JJ, the current susceptibility, is given by a bulk integral. For certain choices of delta chi, which is a parameter we introduce. So we write the function zify in a particular way, which is supposed to look kind of like the finite density zify. You can see that for certain values of delta chi, if delta chi is greater than minus 2z minus 2z minus 1, then chi jj scales with the temperature. If delta chi is less than minus 2z minus 1, then chi jj scales like t to the 0. Then we use the behavior of ZFI, and we see that if delta chi is less than -2z minus 1, then this tau is much larger than the inverse temperature. And so this behavior here, or this tau time derivative, is much larger than any other derivative correction. And so this is a good approximation to the hydrodynamics of the system. And we'll call these two sets of equations relaxed hydrodynamics. Okay. If we look at this, if we look at this plot, we can see that as we lower the temperature, like I said earlier, we are in this regime after the pole collision, and there seems to be a propagating mode. So it's natural to ask what happens if we continue lowering the temperature all the way to 0. And there, we should expect that we find a 0 temperature sound mode. And so what I mean by that is that there's some dispersion relation for the hydrodynamic modes, which is linearly propagating with a real V. And then in this case, there's also an attenuation, and this attenuation is anomalous. It depends on delta chi, which is roughly the scaling dimension of some operator in the IR, or this parameter that appears in the coupling Z of phi. We can explicitly identify each of these coefficients, gamma and V, in terms of the IR quantities chi jj. This CIR is LT over LX when Z equals 1, or it's 0 when Z is not equal to 1, these are parameters that appear in the IR metric, as is L tilde. And what I've plotted here is just a demonstration that this is a good or an accurate description of the relation. So these are all finite temperature results, but each curve is decreasing the temperature as we go up. And then this dashed line is dividing the numerically observed quasi-normal mode dispersion relation by this functional form. So the real part and the imaginary part on the left and right for different values of Z, theta, and delta chi. And you can see that as I lower the temperature, this does a better and better job of describing the quasi-normal mode. And then furthermore, there's a larger and larger region, which is being described in this particular way. And so we wanted to understand what in particular is causing this.
So can I ask a question? So,
yes. Yeah.
So the mode is not linear, is gapless and linear at t equals 0.
Yes.
But because the plot ends at 0.1, right? And
yeah. Okay. So yeah, maybe I'll
from there,
describe this a little better. So we didn't do the calculation at 0 temperature. We did this at finite temperature. And so the question is whether you can see at finite temperature some behavior which is capturing the actual 0 temperature behavior. To do that, you need to look at Ks which are larger than the temperature. And so you can see like here, the behavior might be slightly different. Actually, it's good to see over here on this plot. As K becomes order of the temperature, it no longer is described by these kind of finite temperature equations. The imaginary part starts to kind of come off of this curve, but the real part is still linear in K. So yeah, the point of these plots is to show that as we decrease the temperature, not only do these curves kind of approach this dotted line, which is this form, but they also are kind of spreading out and covering a larger region where this is a good approximation.
Yeah, I think yes.
Yeah. Okay. So there's some kind of emergent gapless mode. It's natural to identify that with a Goldstone boson. And if there's a Goldstone boson, you might imagine that there's some spontaneous symmetry breaking. And so for a long time, we were trying to understand what this spontaneous symmetry breaking was. And eventually, we came to the conclusion that actually there's no spontaneous symmetry breaking. Instead, what's going on is that there's some emergent higher form symmetry with a mixed anomaly. So what this means is, if we go back to the equations that I wrote earlier, here I've written them in a slightly different form, we can massage the equations into these two equations. So on the left, this is just the normal U1 current conservation, which we can write in form notation as the exterior derivative of the Hodge dual of the current J. And this equation we can write as the exterior derivative of some current K is given by minus F. To see how we get this equation, we define the current K, the Hodge dual of the current K in terms of JT and JI, scaled by some susceptibilities. So the dual has one index, which means that the actual current K has more than one index, meaning it's a higher form current. You can see that after having defined this, I can rewrite this equation as the exterior derivative of this star of K with some source minus F. This minus F is the field strength for the U1 gauge field, which is the gauge field corresponding to this current. So this is a mixed anomaly. Sometimes people are uncomfortable with the name anomaly for this, but I think that the perspective, well, people usually call this a Hooft anomaly, and the perspective is basically just that in the presence of a background field, it is an obstruction to gauging this symmetry. So that's why we call it an anomaly. This equation is basically predicting that we can introduce a Goldstone boson, which in the presence of a background source makes the dual of the current K look like the covariant derivative of this Goldstone boson. And so this is an alternative to Goldstone's theorem, where you can have a Goldstone boson because of some emergent higher form symmetry with a mixed anomaly, even in the absence of spontaneous symmetry breaking. Okay, so to get to this, or to see this emergent symmetry in kind of a more physical form, what we did is we took this kind of famous work of Nickel and Son and tried to write an effective action for the low energy theory. So what we do is we take this action for the U1 gauge field. We solve the equations of motion partially. So we solve for the spatial and time components, but not the radial component. Subject to two boundary conditions. In the UV, the gauge field takes the form A bar. In the IR, it takes the form, or at some arbitrary cutoff surface, sorry, R star, we set the gauge field equal to little a mu, and then solve the equations of motion, insert this into the action, and what we find is the action has this particular form, where this is roughly, looks like the covariant derivative of some Goldstone mode in the presence of a background field, which is like a diagonal of A bar and A mu. And we can identify what this phi is. It's just the radial component of the Maxwell field, integrated from this surface R star to R equals 0. So this is essentially exactly what's in Nickel and Son. If we were to forget about the IR, then put the Goldstone boson on shell, solve the equations of motion, what we find is that its equation of motion is equivalent to conservation of the U1 current, where we can identify the U1 currents in this particular form. So they're this covariant derivative with this function C of t, which is defined in this way. And it's just something you find from the action, although later we'll give it some physical meaning. If we forget about the IR, then what we would find is just basically a theory of a U1 superfluid. And we would expect that there's some propagating mode at 0 temperature, which is just superfluid second sound. And its value is just the ratio of this Cx and Ct. But of course, that's not what we should do. The IR is important, and we need to introduce its dynamics into the system. And the way we do that is we solve the remainder of the equations of motion for the Maxwell field subject to the boundary condition that it goes to a mu at r star. And we interpret this a mu as some emergent photon, which couples the IR to this superfluid. So in a little more detail, in the IR, we do the normal holographic prescription. We solve the equations of motion subject to ingoing boundary conditions at the horizon and a fixed Dirichlet boundary condition at r star. When we do so, the IR action has this particular form where in the denominator, we can expand order by order in the frequency, in a small frequency and wave number expansion. And then we can integrate out the photon. Of course, what we want to do is introduce only the IR effects from the horizon. And so originally this r star was arbitrary, but now what we'll do is push r star all the way to the black hole horizon. And when we do that, these coefficients Ct and Cx now have physical meaning. They end up giving us, so here's Ct and Cx, they end up giving us the chi jj and chi rho rho from earlier when we push r star to r naught. So once we integrate out the emergent gauge field, we end up with constitutive relations for the currents. And we find that they have these two particular forms. So the time component of the current is basically the time covariant derivative of the Goldstone, which is what we would expect in a superfluid. But in the spatial part, there's two regimes. So if we're looking at large enough omega, so omega much greater than chi jj over sigma dc, then this term is bigger than this term. And we can ignore the one, these two cancel, and we end up with ji is just proportional to the gradient of the Goldstone. And these two constitutive relations are what we would find in a relativistic superfluid. And so that's the regime in which we should see a sound mode. But because of the thermal bath at lower temperatures, or sorry, lower frequencies, instead, this term is bigger than this term. And we end up with a constitutive relation that says that the spatial current is given by the gradient of the time component of the current. And this constitutive relation is what we typically find in a U1 or a charge conserving hydrodynamics. And so we should see charge diffusion. And importantly, in order for these dots to not be important, we need to have this chi jj over sigma dc be much smaller than the temperature, so that the first thing that happens as we look at higher and higher omega is this term becomes dominant. And that only happens when this chi, or this delta chi, is less than -2z minus 1, which is the condition we found earlier for an emergent long-lived mode. Okay. Written in this form, these two currents should look familiar from what I wrote earlier. They're just the duals of this higher form current. And so now we can understand what's going on, why there's a long-lived mode. There's some emergent symmetry, but because of the black hole horizon, the symmetry is explicitly broken by an emergent photon. So the value of the gauge field on this surface, r star. And because of this explicit breaking, this is similar to the Higgs mechanism in a superconductor. We would expect that the long-lived mode is gapped, but because of the boundary conditions at the horizon being ingoing, instead of giving the superfluid a mass, what it does is it gives the superfluid a lifetime. And so now we want to understand the theory at zero temperature.
Sorry, could you repeat this last thing again? Why it doesn't get a real gap instead of an event?
Yeah, it's because the horizon breaks time reversal invariance, and the way that appears in the in the theory is through the boundary conditions on the emergent photon. Does that answer your question?
No, yeah, I have to think. Thanks.
Okay, so now we want to understand what happens at 0 temperature. And to do so, what we will try and do is quantize the theory only in the IR. And if we do that, what we find is that, well, when delta chi is less than -2z minus 1, as R, the cutoff goes to 0. So we kind of forget the UV part of the theory, and we basically do holography in just the IR, and we take this cutoff surface to the UV. When we do that, then we can see that both of these terms are blowing up. And if we were to insert these solutions into the action, what we'd find is that the action of the IR is also diverging, and so it needs to be renormalized. And it's regularized in the standard way by adding local counterterms. This is a set of counterterms which works. And when we do this, we actually find that there's kind of two interesting features. So now we remember that there actually is a UV. We introduce this counterterm by adding and subtracting it to the action. We subtract it from the UV and add it to the IR. And in the UV, its only effect is to take these functions CT and CX, which seem to have a cutoff dependence a priori. Now it removes the cutoff dependence and sets them exactly equal to the susceptibilities, the charge susceptibility and the current susceptibility for their 0 temperature values. But it also does something more interesting, which is that you can see what we're doing is we're fixing the value of the gauge field on R star, which is this AT and AI 0. But that is the subleading term in a small R expansion. And so we're actually enforcing what we would normally call alternate quantization on the theory. Then if we look at the phase space, varying our boundary conditions or our sources, we can find the forms of the expectation values for the IR operators in terms of the fall-offs of the gauge field. And this is important because this actually tells us what the scaling dimensions of the operators in the IR are. So just like in the holography we're used to, the source and VEV should sum to the spatial or the dimension of the theory. Here in the IR, the effective dimension of the theory is d plus z minus theta, and their differences should be the scaling dimension delta chi, or the difference between the two fall-offs. And that tells us that the scaling dimension of some operator in the IR theory OT has this form, and a scaling dimension of an operator OI in the IR has this form. And now, while we have a scaling theory in the IR, we know the scaling dimensions, and we can just write down a response function for this theory using the scaling form. So what we find is that there's some IR Green's function for the operator OX. It depends on the scaling dimension, delta chi, and then it's just some function of a dimensionless ratio k to the z over omega. And the way that this appears in the IR action is in the standard way. It's just wedge between two, or wedge between the sources a mu. So we wrote things in a kind of peculiar way to match onto the things we had written earlier at finite temperature, but this is basically just saying at quadratic order, you get the IR Green's function. Okay. So
Eric, could I ask a question?
Yes.
You mentioned the alternate quantization imposed by the boundary conditions that you outline in the third line there. You left the dimensionality general. I'm wondering, at least according to a paper by Marov and Ross, the alternate quantization for gauge fields is only possible in certain dimensionalities. So to choose that consistently, and so similar to what we know from a scalar. So there's only certain masses for a scalar in which you have the choice of alternate boundary conditions imposing alternate quantization. So I'm just flipping sources and BEFs. So I'm just trying to understand how this can be generalized in this form without getting into trouble with that.
Yeah. My perspective is that this is kind of a trick we play, in the sense that the theory itself doesn't, I mean, when you include the UV and the IR, this counter term action is kind of canceled. So it's more of a, well, I don't know if I have an answer to the dimensionality, but it seems like this is something that's kind of coming out naturally from the renormalization group flow.
It might be, yeah. So I'm sorry. This is probably a bigger question that we should discuss in the end, if at all, because I think this question comes up several times along the literature, and I'm not sure if there is a conclusive answer. So, but I don't want to derail your talk. So
yeah, it's an interesting
continue.
question because, yeah, you know,
can I
the
perhaps
IR dimension is
interject?
also different. Yeah.
So in the Marolf and Ross paper, they really are talking about the multi-trace deformation or alternate quantization in ADS spacetimes.
Mm-hmm.
And here you see that the IR spacetime is not ADS. And also the gauge coupling is running, parameterized by this exponent delta chi. And so that's what allows us to find that alternate boundary conditions are allowed more generally than in the cases that Marolf and Ross were looking at.
I see.
But of course, if we took a limit that's reduced to ADS, to the case that Ross and Marolf had looked at, then we would find the same as they did.
A restricted range where this boundary condition could be chosen.
Yeah, exactly. Here you have to imagine that to go back to Marolf and Ross, if I'm not saying anything wrong, then you need to set delta chi to 0 and z to 1. And then D would most likely play an important role on whether you can have those alternate boundary conditions or not.
That's interesting. Thank you.
Okay. So in the last couple of minutes, I just wanted to talk a little bit about, we spent a lot of time trying to understand the zero density case because it's a model that we can kind of do a lot with. We can solve the equations of motion analytically in terms of the bulk functions in a nice way, write down an effective action and kind of see how that effective action describes a superfluid coupled to some quantum critical IR through an emergent gauge field. And we expect something similar to happen at finite density, but there's some kind of key distinctions and interesting things that appear. So one of the things that happens at finite density in a translation invariant system is that we should have some first sound mode. And this sound mode also survives to zero temperature, but this is a different sound mode than the superfluid sound mode. And so in some sense, for instance, in the probe brain case, you can see two different regimes where in one case, there's kind of sound modes which collide on the axis at finite temperature, or for small alpha prime, there's a different type of sound mode. Here, I just want to make a distinction that the superfluid sound mode, or the second sound mode type behavior we saw at zero density, also exists at finite density, but it's distinct from something like the first sound, which is more like the small alpha prime part of the probrane. Furthermore, the sound speed of the second sound mode is not universal in z equal 1. It depends on the UV choice of sources, whereas at finite density, it's always given by CIR squared over d minus theta, which is what we would expect in a superfluid, something that is actually just set by the dimensionality, and the CIR is basically the scales of space and time that we fixed. Furthermore, at zero density, we picked this value of delta chi because we wanted the DC conductivity to diverge or to be dominant, and we actually find that the time scale for the relaxation of this incoherent mode is given by the same scaling as the DC conductivity. That's different than at finite density, where you still have a long-lived mode when delta A is less than 0, but it's slightly different. It scales slightly differently than the DC conductivity. And the reason is that at finite density, the incoherent current susceptibilities and incoherent charge susceptibilities also have temperature dependence. And if you remember, this tau is given by a product of, or actually the sigma DC over chi JJ. Whereas in the zero density case, chi JJ and chi rho rho scale like t to the 0. And then there's one final interesting feature for the finite density behavior, which is that as you go to zero temperature, it seems like the quasi-normal modes are piling up rather than having a sound mode with some anomalous attenuation. Instead, what you have is a branch point which starts at omega equals Vk. Everything I've said is, well, it's interesting because it's appearing simultaneously kind of in the condensed matter literature. It might have sounded weird to talk about an emergent higher form symmetry with an anomaly, but with a mixed anomaly. But it turns out that that same language can be applied to Hamiltonian systems or systems on a lattice, where if you have a translation symmetry in the UV, well, in the IR, the lattice disappears. And so that translation symmetry kind of morphs into an internal symmetry. It turns out that internal symmetry is a higher form symmetry. And then if the system is compressible, meaning that I can add charge to each lattice site continuously, well, that also should appear in the IR of the theory. And it turns out the way that that happens is through a mixed anomaly. And so it seems that compressibility plus translation symmetry for Hamiltonian systems is related to emergent higher form symmetries with mixed anomalies. And I just want to point out that in the systems that we investigated, we can continuously tune the source of the dilaton in the UV and end up with the same IR physics. And so in some sense, what we're doing is we're changing the charge on each lattice site, said kind of vaguely, and still ending up with kind of the superfluid dynamics in the IR. So this is just kind of food for thought, but it is related to this question of why there's this, or could be related to the question of why there's this line of quantum critical points in the cuprates. And then the last thing I wanted to mention is that I started this talk by talking about a linear in temperature resistivity, and I came to the conclusion that a linear in temperature resistivity meant a time scale which scales like 1 over the temperature. But it turns out that that's not necessarily true, because in these systems, the resistivity is actually given by a product of the incoherent susceptibility times this time scale. And so if chi jj scales with temperature, as we saw it does in the finite density case, then you can have a conductivity or a resistance which has a different temperature scaling than some long-lived mode's lifetime. And in the condensed matter literature, this has been called critical drag, but I think people have kind of been understood that this can happen if you, for instance, renormalize the effective mass in a Fermi liquid for a long time. Okay, so here's some conclusions. We've seen power law DC transport in the cuprates, both in the Hall angle and in the resistivity. If we were going to try and describe this with the scaling theory, we would see we need at least 2 scales. But there's an assumption that there's no long-lived mode. And so the whole theory can be described from a simple scaling analysis. In these Einstein-Maxwell-Dilaton theories, we see that we can get scaling behavior, but in general, there can be long-lived modes, and when there are long-lived modes, they can give rise to a different scaling theory in the IR. And we can understand the emergence of this long-lived mode as the emergence of some generalized higher form symmetry, which has a mixed anomaly with the U1 in the UV. This higher form symmetry is explicitly broken by some emergent gauge, which couples to the black hole horizon or to some quantum critical bath temperature and ends up giving the emergent gauge field some lifetime, which appears in the DC conductivity and ends up giving a very large DC conductivity. So with that, I'll take questions.
Thank you very much, Eric, for a very nice and insightful talk. Questions? So there was one question in the beginning that I had not seen directly. So about 18 minutes into your talk, in the cuprates, specific heat and entropy is linear in T. And the question was, does this sit well with Z equal 4/3, D equal 2, and the theta equal 0?
Yeah, if I remember correctly from, let me go back. If I remember correctly from this paper, I think that it does work. Yeah, I'd have to go back and look at this paper. I mean, the starting point of this analysis was just to look at the scaling behaviors of the Hall angle and the resistivity, but then after they found these scaling exponents, they went and checked those against other measurements, including, I think, the specific heat.
Yeah, I remember there's some relations. I think one is the hyperscaling relation, and so there's certain relations that between these coefficients that's, I guess hyperscaling is not the best because that can be violated, but there are some examples where these are related to each other through certain equations, and so I suppose one could more generally ask if the values that you give here in the box, if they are in agreement with all those relations that are known. I suppose the authors would say yes, otherwise it wouldn't make sense.
Well, I think there are certain,
if you look back at the Hartnell and Karsh paper, they are explicitly saying that there's some tension with the thermodynamic sector.
Oh, okay.
The specific heat goes like T to the D minus theta over Z. So if you set theta to 0, that's D over Z. And since if you take D to be 2 and Z to be 4/3, then clearly there's, I mean, you're not getting 1. So, I think cuprates are one thing. In the case of holography, we're a bit more modest, perhaps. We're just trying to get some consistent scaling theory that describes this particular strongly coupled quantum state. And then you see that you can do that consistently in this fashion. What's going on in cuprates, may or may not be related to that.
Yes. Yeah, I remember there was a discussion about kind of phonon physics in this paper, maybe being slightly different than.
Yeah, I mean, it's not entirely clear that everything will be controlled by the same type of relaxation.
Right.
Ideally, it should, but okay, who knows?
And then there's a follow-up in the chat to that. The correct answer is no. The exponent found in the cited paper, I think that's the Hartnell-Karsh paper, 1501. The exponent was d minus theta divided by z. I think that's what you also say, Blaise.
Yeah. Yeah.
Mm-hmm. Okay, yeah. So there's definitely some tension that needs to be understood, it seems like. Are there more questions? More questions? Well, if there's no more official questions, I remind you that afterwards we stick around for a minute to just talk off the record and chat a bit. But before we do that, let me thank everybody who asked questions during the talk. Thank you, Eric, for creating an interactive experience and an insightful talk. And we are looking forward to seeing everybody next week. Thank you, Eric.
Thanks.